Good morning, everyone. We are Team Lunar ROADSTER. Welcome to our string validation demo. The team consists of me, Deepam, Bhashwant, William, and Simpson. We are advised by Professor Greg Whittaker. The motivation for our projects stems from the lunar polar highway. As you all know, humanity is returning to the moon, and most of the missions are focused around the polar regions. The yellow line indicates a path that could connect most of these regions of interest to a traversable path. This path that you see circumnavigates the moon at a certain latitude. Hence, we want to build a road or a highway that could circumnavigate the moon, and rovers with low mobility could traverse it. The question we're trying to answer is it possible for a solar-powered rover to traverse this path while always maintaining sun synchronity or never encountering the sunset? Why would you want to maintain sun synchronity? On the moon, as you know, solar energy is much more powerful than on the Earth. So any solar-powered rover could sustain its entire operation using solar energy alone. The sun synchronity is possible on the moon because one lunar day is equal to 28 Earth days. So take an example of 75 degrees or 80 degrees latitude. You only need to go jogging speed to circumnavigate the moon. However, the moon is not that traversable. We want to create a path that is flat, circular, and traversable to allow us to circumnavigate. That is where the project Lunar ROADSTER comes in. It's an autonomous moon-roving rover that is capable of finding these exploration routes and grooming traversable surface trails. By grooming these trails, rovers with lower mobility capabilities can move from sites to sites, such as human habitats, mining, and other exploration sites on the moon. This is our primary use case. Taking a reference latitude, as you see, there's a lot of craters on the board. So an original traversal path would look like this, where you would have to navigate around these craters so that your rover doesn't get stuck. We bring in our project Lunar ROADSTER. The first thing that we will do is identify which craters can be groomed and which craters you would like to avoid just based on size. So for example, that crater is something you would like to avoid, whereas those two craters are small enough for us to groom. Therefore, it will generate a groomed path that would look like this, ending in a more circular path than a circuitous path. Today's demonstration will be divided into two parts: the pre-demo setup and the actual demonstration. The pre-demo involved getting the ROADSTER ready, setting up our external infrastructure, setting up the moon yard, and mapping it out. Using the map, we planned an optimal transport path to groom these craters. During the demo, we'll be switching to autonomous mode to groom a single crater, and we will also be demonstrating some teleoperable capabilities, some mechatronic capabilities, and the pushing strength of our rover.
So I'll walk you through the hardware of our ROADSTER. Up front, we have a custom-designed dozer blade for efficient terrain manipulation. We have 4 3D printed wheels for maximizing traction on loose, uneven terrain like the stand we have over here. The entire system is powered by 3 20-volt batteries, and the entire compute is carried out on the NVIDIA Jetson HGX board over here. On my far left, we have a total station that continuously tracks a Leica prism for global positioning. And finally, we have all the electronics set up in this clean, compact electronics box. So we set up our moon yard, which is our physical testing ground. We dug out a crater, the kind of obstacle our dozer will encounter on the moon. So this will be the focus of our growing task today. So in order to give our ROADSTER a complete view of the environment, we mapped the entire moon yard using a Faraday laser scanner, the device that you can see in the picture over here. This device gives us a high-density point cloud map, which essentially forms the base layer for our planning and navigation stacks to act upon. For the external infrastructure, the Leica TS16 total station continuously tracks the Leica prism and gives us the XYZ values related to a fixed frame. And we fix a fixed frame over here. This is a map frame, but this is the X direction, this is the Y direction, and Z points upwards. So once we get the XYZ values relative to this, the data is sent to the Jetson for localization using the TX2 relay, the box that you can see on the right-hand side, and it does this using the land routing. So as I mentioned, this is our frame. Also, when we spawn the rover in the moon yard, we have to calibrate its yaw in order to ensure that the IMU data is relative to the map frame itself.
Using the point cloud, now we generate an optimal transport plan. So our goal objective is to grade this crater that you see. So we set up a cost function that minimizes transport distance as well as transport volume of the sand. Using this, we generate what we call transport assignments. And using these transport assignments, we generate multiple waypoints that the rover will use to follow this path. So beginning with our demonstration. The demonstration here, the rover will autonomously follow a straight path through the crater and groom it in a sequence of front plate and back plate. The way the behavior tree works is once we map the moonyard, it is sent to the rover, which is the update map. The rover will say that we have explored the environment because it has a map. Further, it will use this to plan the transport and get transport goals. The get transport goals are the waypoints generated in rover ports that are then sent to the navigation stack. The navigation stack will generate a path that the rover will follow, as well as generate when and where the tool will move up and down to enable grading of the crater.
So while the rover moves, you can also observe the visualization on the screen on your right hand side. So you can see the body frame of the rover moving, and the arrows that you see are the goal poses that we get from the transport plan. So I'll just walk you through the sequence of actions that will follow. Right now, it's moving towards an offset position, a certain distance away from the crater, and it has reached a position. Next, it will move to the source position, which is this near the crater there. And once it reaches this position, it will move the dozer blade down and then push the sand into the sink, which is near the middle, the deepest part of our crater. Once it does this, it's going to lift the blade up, move forward to the other end of the crater, the other end. It's going to put the blade down and then back blade. So while this happens, I'll talk a bit about how our robot localizes. How does it know its position in the moonyard itself? So to facilitate this, we have three sensors. The Leica total station gives us the XYZ values, the position with respect to the map frame. We have the vector nav IMU, which gives us the linear and angular accelerations, and the wheel encoders give us the wheel velocities. The data from these three goes into a global localization node, and the data from the IMU and the encoders goes into a local localization node. Both of them run an extended Kalman filter, and together they give out the pose of the rover, which is its position and the orientation with respect to this map frame. So right now it has reached the same position. It's going to go forward next and then back here. So while it does this, I'll talk about our autonomous navigation stack. So the Roadster has a navigation stack running in real time. It uses the goal poses obtained from the transport planner as the targets, and it plans its own set of waypoints. So in this visualization, you can see the plot in blue is the global plan path that we get from the navigation stack, and the path in red is what the rover actually follows. So the 15-second, we have 15-second pause to ensure that the dozer blade goes down, and now it is backblading. So backblading is a novel feature for us. It allows us to fill up a crater much faster. We can finish this in just two passes, the front and the back. So we don't have to tackle a crater from multiple locations like you would have seen in previous projects.
Next, we will be moving on to rover capabilities demo. While that gets set up, I would like to show you some before and after work that we have done and improvements we've made to the Roadster. When we got the Roadster, this is what it looked like. And based on our improvements, this is what it looks like now. The clear improvements that you see will be the wheels, the electronics box, a better tool, and overall a much more finished look to the Roadster. Beginning with, we had stock rubber wheels which were compliant and focused on generating grip through interaction with materials and friction coefficients. Now we have 3D printed wheels that focus on wedging to generate grip, coupled with higher torque actuators which generate the traction we need to push the sand. Next, when we got the Roadster, it was a cluttered wire mess, and there was a lot of unreliable connections and inefficient designs to the e-box. Now we have a compact PCB inside the e-box and in an enclosed design that gives us reliable connections, as well as gives us a more efficient space use and a more finished look to the product. We improved the power distribution board. The power distribution board on the rover focused on eliminating voltage noise and also used screw terminals. Now we have a custom PCB that does over voltage protection, reverse voltage protection, as well as it has XT60 terminals. This allows us to have ease of assembly while maintaining reliability. Next, the tool that we had used to be that size. It was a central grader. This allowed them to get more control of the tool as it was in the center of the chassis, so it didn't pitch as much. However, they had to go inside the grader to fully grade it. Further, now since we have the frontal dozer, it is first of all you're allowed to make the bit much wider. As you can see, it's about 3 times what it used to be. And since it's on the front, we're allowed to be able to relate craters while maintaining all four wheels on the ground. Further, we're working on getting the teleoperation demo set up. So if anyone has any questions at the moment, please feel free to answer.
Sorry, can you discuss a little bit more kind of the strategy for building a printer from energetic standpoint and energy and time, I guess? What does this exactly function look like?
So, okay.
Yeah.
So our cost function minimizes transport distance as well as volume. So if we have a higher transport distance, we need to expend more power to get that transport, as well as if we have more volume, we're pushing more sand. That means we're pushing more energy. So if our objective function is able to minimize these in an optimal path, that means we have most energy efficient path movement, which is what we're trying to accomplish.
Okay. Is this actually active? Is this something that, I'm sorry, where is the decision made? Is it to look at the initial map?
Yeah, so we look at the initial map and then we run through the entire map. There also the map when we assign something called a source node in a sink node. A source node is something you would read as a source of sand. A sink is where you want to fill sand. And then based on the cost function, it optimizes the source to sink point, which is what per essentially per node, and then we average it out, clean it out, and then get an optimal.
I see. And that's how you get to how fast you're gonna do or how you're gonna. I guess from the volume, what does it mean you manage the blade in a different way? What would be the translation process to how you manage the blade?
Okay, so first thing it will do is basically identify which point on the rim has a hard sand. For example, in this, the approachable distance, that area had the most sand. So if getting to get the minimum manipulation, you would want to use that part of the rim to fill the sand. And if you had too much volume, you would move it a little bit up so that it doesn't get stuck based on what our pushing capability are.
Follow on this, if your crater is significantly larger, you then in your plan avoid going into it, because it's too deep and then just only push from the outside.
Yeah, so currently that's what we talked about in the beginning. If it's too big, we're not going to be doing it. That's what we avoid.
Okay, so you're only choosing craters that are small enough so you can actually go across them and then get the back part.
And you don't do techniques like skimming, like going to the top and a little bit more coming back. This technique of pushing, stopping tight, half point across, and lifting, driving, backfilling. That is kind of the main goal, where it's.
In the fall semester, we're looking at implementing a validation as to how much you've actually achieved versus what we wanted to.
Okay.
And then we might add the second part.
Next, we demonstrate the other roadster capabilities, starting with teleoperation. Our dozer operator Deepak will show you this. We can wirelessly operate this using the joystick. We can move the robo front. We can also steer it left and right. And the dozer blade can also move up and down. So we configure the joystick such that every button press increments or decrements the dozer height by 10%, which corresponds to a 10 millimeter increase or decrease. So this allows, we have active steering, which allows us to control the front and the rear steers, and enables us to make sharper turns, which is very important for reversing in uneven terrain like what we have over here. To show you the dozer actuation strength, I place my foot directly beneath the dozer plate, and as we push down, it's going to lift the front wheels up. This shows the strength of our actuators. This is very important for performing terrain manipulation effectively. Next, for the dozer pushing strength and the stator grooming, we're going to fill up the stator and we'll demonstrate it that way. So right now we will move the rover till the rim, and once it reaches the rim, we're going to put the dozer blade down. So once it's done, we're going to push the sand into the sink position, the middle of the stator. So once it reaches the rim, the center, we're going to lift the blade up. We're going to move to the other side of the crater, and now we'll perform backblading. So this backblading allows us to get a much cleaner path, a traversable path for our rover and helps us do it faster.
Moving on to some of the results we'll be showing you today. We will talk about the mechatronic capabilities of the rover and building a machine that can actually push sand in an environment like this. We will talk about some localization and autonomous navigation results, as well as identification of the craters we want to avoid in group. So in the beginning, we have a 60-centimeter tool width. Oh, also, if anyone wants to operate the roadster, please talk to Deepak. He'll teach you something and you can do it while we do this demo. So it has 60-centimeter tool width, which is 3 times its predecessor. This, we also have much more increased tool actuation strength. We also upped the drive actuators, which allowed us twice the torque, and the wheels allow us much higher input, which give us the pushing power we need to actually create these craters. Further, we have an organized electronic box, which gives us reliability and much more efficient power distribution. Overall, the Roadster is an optimal, specialized machine for crater geometry on the board. Since we just had a successful demonstration of the autonomous grading operation, we have a video, but we'll be skipping over this now. Coming to the performance requirements, our performance requirement 1 being that we will plan a path with a cumulative deviation of less than 25% from a chosen latitude set. Since for our string validation demo, we are tackling only one crater and that in a straight line, the straight line becomes the ideal path, which is also our planned path. So this performance requirement is not applicable. We'll be tackling this in the fall semester. For performance requirement 2, the rover will follow a path within a maximum deviation of 10% of the planned path. So in this visualization, the plot in blue shows the global planned path that we obtain from the navigation stack, and the plot in red is what the rover actually follows. We then calculate the per point distance, the deviation, and we get the cumulative deviation, and we found that it's less than 10% for all the tests that we conducted so far, with an average of around 5% deviation. Our next performance requirement 4, to show that we will avoid craters of size greater than 0.5 meters in diameter. We previously set up the moon yard with multiple craters of varying diameters, and we mapped it. Then we ran a script that basically identified the large craters of size greater than 0.5 meters, and it ultimately gave us the centers of only the gradable craters, which in our definition is a crater of diameter less than 0.5 meters. Our next performance requirement, to show that we can fill up craters up to 0.5 meters in diameter and 0.1 meter in depth. We just demonstrated this twice, one in full autonomy and the other in teleoperation. So this is a video, and this is our before and the after. So we are on the path of joining our fellow rover Moon Ranger in the Artemis missions to colonize the moon. So thank you, everyone. We are Team Lunar ROADSTER, and we can take up any questions that you may have now.
Good job. I do have a couple of questions. One is, and I didn't press you guys on this, maybe I should have, but you have a quality spec for the efficiency or goodness for fusion filtrated.
We do have a performance requirement that we're not tackling this semester, but we have a maximum slope that we're targeting. So maximum slope of 5 degrees is what we will be targeting in the fall after we implement our validation.
Then you just talked about the avoidance of larger craters. But if I understood what you described, it sounded more like you tested the identification of it, but we actually have the rover plan a path that avoids them.
Yeah.
So from the map that we obtain, the tool plan, so we will get the centers of only the gradable craters. The map itself, once we get it into the rover, will avoid the larger craters and it will give us the goal poses of only the gradable craters.
Okay, but I mean, have you done that at least in simulation, or just shown one way or another that it will do the avoidance? The plan is going to plan around with that.
Yeah, so we actually took all of these waypoints and we basically tested the simulation and was able to avoid large size craters because we only get the coordinates of the gradable craters. Waypoints are generated on only those centroids.
Okay, it'd be good to see a video of that at least. Right? Maybe you don't have it now, but on the floor. Sure.
Yeah.
Last thing, it's not anything you guys need to worry about now, but I'm just curious. I know that previous teams have dealt with this. You got the Leica that's doing the localization. What's the plan on the moon for localization?
Okay, what's up, Taco? So we are planning on using a camera that looks upward so that we look like using like stars. So it mimics a star from structure.
So we're planning to use the lights that you see above you to basically try and map out the constellation that we try to get absolute Gaussian orientation. That is something we'll target next month.
We also plan to use maybe visual photography to track features within the moon here. Our plan is to get rid of the filtering station. Yeah, come with a better localization.
Do you plan to do as a follow-up? You plan to do when you use visual along the base?
No, so in the fall, we're improving our localization task that, but we haven't finalized on the method yet. The idea was that in the spring, we're able to get our mechanism ready, get the base MVP ready, and then we'll work on refining our product.
Also, on the metric of completion of the job, like you mentioned, the swap, the swap. I'm just wondering if that's the right kind of metric to use. Versus something, you know, you're filling a volume basically, and then you look at smoothness, you want to create some growth, right? So you want some growth that is it just the slope, or maybe are you thinking of other metrics, additional metrics to quantify the filling of the craters?
We can look into it. At the moment, we were defining it something as reversible. So on average, if what we found is a normal rover could travel a 5% or 5 degrees slope. That's what we define the metric based on. But if we do look into making it more refined, we can have a discussion about that in the fall.
I think that's a really important point, just because you're not just creeping. For this kind of a route, your speed. And, it's just a lot different than what they would have. In the autonomy, drive, we saw right from the beginning. Your intent path was straight. But, there was, some visible weaving. What's that about?
The partial swaying, the snake-like motion that you may see is due to errors, latency errors in the roaming station, and also the fact that our IMU is not the fanciest one out there. So this is why we plan on coming up with a better localization method for default semester. So this basically helps us lay down the problem statement for the next semester.
And adding on to that, the cable panel is using the A-star algorithm, we will just generate a straight path without considering the robot dynamics. And for local panel, we are using NDPI, which takes into account the active and steering model, and that's the reason you see a wavy path.
Yeah, because there is a relation, you have a metric about 10%. Right, and then given the size of the craters you're aiming for, I think optimizing in relation to the task, it's going to be very important. Otherwise, you just, and then because you also have the speed, it's a metric, it's a key metric as well. So how do you manage the trying to get the craters localization and basically deviating very low from the path and doing it at a higher speed, etc. All these things going to be critical. And I think this is we think what you can do in the fall. So.
We got 7 minutes, 6 minutes maybe. So we keep doing questions, but it'd be great to see at least one more auto, like maybe that crater. We try and grade that one.
We'll have to remap that we can't do it without remapping the Lunar at the moment. Yeah.
So you don't have that one in your map already?
No, we don't. We only map that one. That one was to actually for people to play around with when we handle the
Tell you.
How long does remapping take?
So each scan takes 11 minutes. We need to take 3 scans, and also none of us can stay in the area during the mapping.
I was wondering, are you guys the first machine or just like whether you guys not?
So the objective is to fill the crater. So the rim that it approaches first is what goes into the deepest point of the crater. And then we use the other rim to fill out the crater. Is the idea. So the rim usually on the moon is equivalent to approximately equivalent to volume of the radiator sun. So we're using the entire range of the volume.
Yeah, I take another cut at it. So, I have a great bulldozer and I bulldoze all the time. And, if anybody here gets on the bulldozer the first time, that, your ability to control things when you're going forward is, not good at all. Takes a learning curve, a lot of skill. If you're backlighting, you put it down, turn it in reverse, and it's a beautiful flat finish. Yeah, I just mentioned that, we call it a rover sometimes. It's a bulldozer, very good one. I've seen your platform before be shaky and not have almost the power traction just to drive itself around. And just watching it today is pretty very good step up.
So on that note, maybe the answer is no, but this isn't quite flat. It was originally mapped. We do more, or maybe the question is, does your autonomous algorithm have any feedback now to say, hey, this isn't quite flat? We need to do some more work.
Not yet. That is the validation we will handle for.
Okay. But if you set it loose again on this, will it do some more work, or is it just programmed to go once forward and once back?
Currently, just one forward, one back. So it'll just probably do the same motion again, because according to it, the operator is still there, because we use the same map that we used in the beginning.
Okay. But he said, sorry, well, thing is, I'm not putting that together with what you were describing as what seems to be a more complex algorithm, figuring out the volume. Out of this job.
So because there is no feedback of the map, so it doesn't know the map has changed because we haven't revamped it.
Right.
They aren't using an active mapping method at the moment for it to know that it has done.
Okay, you've only been doing that in sim.
Yeah.
Sorry.
Well, you have an arm that reaches forward and a sensor that is up there pointing in front of the blade. Is it even turned on?
Currently, no, it's not going on. We have implemented the code for this. We plan on using active mapping for example.
That's gonna be the trick, that's gonna be the means to determine if, that's the standard, standard.
Currently, we don't have a feedback of. Sorry. Currently, when you're trying to put the data, you don't have a feedback of whether the data is filled, right? So, when you do, when the robot does it autonomously, which is goes in speech once, your feedback is visually, okay, so, this is going to go standard and push, post onto the standard.
Not standard, is what we get from our optimization algorithm.
Okay, yeah, it's a fuel value. And in case you like,
So optimize, we've explained the reason. So the idea is that we want to minimize transport volume and transport.
okay, right.
So based on that, how we set up our cost.
Alright, two quick questions. One is, I'm assuming this is a piece of you that you have like currently.
Yeah.
For e-box, right? And then the other question was, so, Red mentioned that, like, obviously you've got a lot more traction, you've got a lot more power to like move soil, and like, obviously a lot of that is to do with the size of the tread that you're using. When you were designing the tread, how did you decide what size the tread should be, or was that just, you tested this?
We went to 5 different designs, tested them, eventually ended up on this around what we want to use for them.
So did you try treads that were like deeper?
Yeah, we have different multiple ways. Yeah, we have not actually that converts to this.
Another question, sorry. No, well, just on that one, tread is one thing, but once you have wheels that can dig and develop traction, the next thing is not having enough gearing to drive it. And I was really impressed when they dug in and changed the gearing of this thing. But it's a small, very specialized machine.
Yeah, two quick things. The first is, and we have a video actually with rocks. So what happens if there are embedded rocks around the rim or around the crater, basically, or where you try to close?
We don't have the visual feedback yet. So currently in the environment, we don't have rocks. We just kept them around to make it look like a moon. But we don't have, we're not targeting rocks at all.
Okay, maybe a different way to put the question is, even if the cohesive say of the regolith is different and gets it's a little bit more cohesive say, it will be finding more resistance. What I was getting to is, do you have a control algorithm that kind of says, okay, this is too much, I'm going to raise the blade a bit, then continue, then come back and do it, or is it just two passes forward and back and you're done, whatever it is?
Currently, just forward back to the moon.
Okay.
But what if you wanted to, make it, how would you do it?
So we reduce.
Yeah, so I can take that up with respect to the dozer assembly itself. We have the linear actuator up there. Currently, the actuator that we're using, it only gives us the position of the stroke of the actuator. But we are planning on checking out other actuators that can also give us some feedback on what the current draw and what the current draw is basically. So when it crosses the threshold, we can ask it to go up, maybe not too much, but a little, so that it encounters less force and hence less pushing force.
And you don't have anything on the blade?
No,
force.
we initially explored that idea of putting some sort of load cell on top of the blade. We weren't able to integrate that, and we see, and because we actually after traction so much, we didn't face that problem. So if we do target craters that are deeper or rings that are higher, we need to include that data. Yeah.
The last point, because we're running out of time, is there have been a lot of studies and there is information on the density of certain types of craters and sizes of craters. David cares, a whole bunch of people have written about that. It may be worth looking in, maybe it's beyond the scope of what you're doing, to create an environment that kind of simulates, let's say, a typical lunar surface. You may be dosing more craters, but smaller ones, which may be a different concept of operation. I don't know, just consider that.
Yeah, we did actually plot some, we looked at some data and plotted some simulated lunar environments that have like one big crater, two couple small craters, which we'll be using in the fall. So we'll have logic for that. We've written that code. It generates basically randomized moon accurate maps for the moon, which we'll be using.
And we scaled all of that down to the size of engineering.
All right. Don't want to keep you guys on the spot too long, going 3 minutes past. Thanks.
I didn't see photo of all of you.
Sure.